let's solve this set theory problem, prove this relation. X, Y, Z are presets, and X interaction with Y minus Z equal to X intersection with Y and minus X interaction with Z. So we just have to prove that this holds. We can have two approaches. Okay, let's use the Venn diagram. I believe that if you any of this approach for this course, if you use Venn diagram, I think I will accept. But I would want to show both methods to have this problem. First, let's do the Venn diagram. So let's see if you okay, this is one of the solutions. You remember that's what we're supposed to do. So if you go left hand side, if you just work through, you have to demonstrate. Okay, let's see, X is this pink or red area, and Y minus Z, so Y is this green circle and Z is this red circle. So the Y minus Z, which is those Y that's not in Z, that's shaded in this yellow area. See, this Y, take away Z, so it's like a moon, so this one. And then that's easy, straightforward. X and intersection Y minus Z is this yellow area and intersected with this red area, and that's this shape here. All right, so now I just illustrated down here at the bottom this. All right, so that's left hand side. We remember it, this area. And on the right hand side, we still have X, Y, Z, but we just do differently. X and Y intersection, which is this kind of like a football, yeah, like this, shaped kind of like a fish, and this X and Y. And X and Z, and then this blue and red, so this one. So they are intersection, no. We want to subtract that. So when this take away that part, and then we end up with this shape. So even though we go through different paths, we end up with the same area. So that's the proof that they are the same. Okay, convinced? Now let's work on the using mathematical expressions and logic identities. Right, let's prove formally with logic, symbolic logic. So we can do whatever approach, but the final goal is to convincingly make left hand side equal right hand side. Let's work on the left hand side for now. So xz minus y, and if there is a substance will be element belong to x, and at the same time belong to y, and of course, and then y minus z, so parentheses, and not belong to z. That's simply because using the definition. So, and then we use logical rules, the exchange rule. Actually, we can remove this parentheses, and then simply left hand side equal to 3 continuously. X belong to y, and x not belong to z. So that's on the left hand side. So another approach is, in fact, there is some errors, is from the right hand side. We can show the right hand side is this, will be okay. So now look at the right hand side. So what is this? Okay, that, and in fact that is equal to directly, we must, every step you must have explanation. If you don't have explanation, I will deduct at some point, because this is to be proved. We know it's right. You say, well, this equal to that, and of course you're right. But if you're missing the explanation, so then you're not fully complete. So here of course is the correct proof, but I see a lot in the homework, and so this, by the definition, it will first simplify to this. So here, let me highlight this part to another color. Okay, remember? So that first part, x elements belong to x and elements belong to y, obviously, and it would be minus, which simply means x not belong to the intersection of y and z. Alright, so then now let's do a Venn diagram of this part. X, okay, this is red, green one, the red one is x, so that's x. So then that one is z. So this part, okay, this part x not belong to y and z are the intermediate part, are in the middle part, and not belong to is actually the shaded part. Agree? So x not belong to, so not belong to this. So then, and then the some of your solution, you directly write down this. So then see, notice this part, the first part is same as this part. Okay, looks like the implication of the, now this part is x belong to yx and y x not belong to z. So simply remove the parentheses. So you put this in, so that's not correct. So if you actually do this, this part is not directly equal to that part. So looks like, okay, this equal to that. No, that's not. You see that? All right, so you must see or say this second part. Okay, and this part are the same. So this are exactly the same, but this second part, and it's not the same. So you see, so then x and z again, and we're working on this Venn diagram. X belong to x, but then x not belong to z, and then here. So it's this part. See, they are different. So therefore, you cannot simply convince that this is that. Of course, but then is that wrong? Now, well, if you claim this equal to that in your homework, or imply that equal to this, that's wrong, because you see, that's this, these two obviously not the same. However, the final result is still correct, because so the intersection with this part and with that part is still correct. So, which means this part and that part is not correct. So that's the interesting. Let's put the y here. So now let's put y in green. So then put y in here. So now let me put y in here. Okay, the green is actually y. The green is actually y. So now x interaction with y is this part here. So then their interaction, their intersection with this part is none other than here. So x, and that's y, and with this part. So then it's this part. Okay, let's go look for the top. So x and y interact with y, and is here interacting with that. So that part is eliminated because that's not in x. So it's still in this part. All right. So now that's the beauty of, that's difference from set theory and regular algebra. You would think, well, you're claiming this part equal to that part. No, it's not. Okay, it's not. But their total effect when they do the intersection with this and that, and finally end up with the same. So even though this looks like this part like that, okay, it's multiplied with this part, this will equal that. No, this is not equal to that part. But the intersection with that is the same. So the final result is still counted as correct. But if you didn't explain this part, I don't count you correctly, because you write something that you didn't explain. Its formula is not, you say, well, this equal to that, and especially many of you doing the same, have the same mistake. So this equal to that. If you just write down that, and also Some don't even write this part. I put this part in. Some simply without this part. Okay, just directly write from here to there. I don't know how did you get there, because so even though the result is right, but this, which means you didn't explain the idea. So it's not this part equal to this part, and definitely this part is not equal to that part. Okay, and so then that's, you are supposed to explain this way. Now let's look at the formal way of how you directly use the set theory to do this. Okay. First, let's look at a typical mistake of this question. We go from, of course, we try to go from left side to the right hand side. If you see this left hand side, we will have this. I can easily expand it as that, right? And then, of course, using idempotent rule, if you recall, and you say x and x equal to x, you can insert as many x you want into here with the exchange rule of and, insert another x, so you can easily go here and negative z, and then that's obviously follow the rule, correct? And then of course we try to prove that this is finally this. So looks like very amazing. Okay, that if you write that you directly write down this, that's correct. But that doesn't mean you, and sometimes if you write down this, you write down this is not correct. That doesn't mean this equal to that. So that's what I'm trying to say. So you must show that this actually, which means this is not that. It's not a negative. So see below. Okay, and so that's not, if you go this way and you directly write down that, and I would not totally get it wrong, but I would say, well, you get only partial credit, and you're not getting the full credit because you go that and then this, sort of this equal to that. You have to explain why this, even though the indeed is all, in fact it is this together equal that, but doesn't mean this equal this. All right, so x intersection with negative y is not equal to that. All right, now let's see what the full proof, formal proof is. Sorry about the sketches, but you really have to really see the points. So we go from left hand side to right hand side. So left hand side, we try to go to the right hand side. You just use the symbols and logic or set rules. And x and x minus z, right? And then it should be equal to, so that's the x and z, not z. X intersection with y and not z. So that's the, but then we can add or a null or zero, means zero or anything will still be zero. So we insert is or here, and so that's 0. And then now if you forgot, let me remind you where I'm based off. So 0 or anything, it was 0, but here I just insert a 0 to here just to rearrange this. Now how you get an intuition to do this? Well, exactly come from those Venn diagram we worked out. So it's a 0 and that's 0, the same thing, but then 0 equal x and not x. So that's called, what do we call it? That is called inverse law. So that inverse, so, and add inverse, the same thing, but now you use exchange rule, and then you can exchange order. So, oh no, commutative rule. It's not exchange, commutative rule, x, y, and x is the same. So you can move to whatever position you want, as long as an end, but I would x and y. On the second part is also x and y. At this moment on the left hand side, this area is actually nothing, because or then. But now I took this underlined and this is underlined. Using the distribution rule, I take this out. So you can say x and minus z, okay, and then x and y. So then, so x and z, not x and not z, and not x and y. You work carefully, okay? Actually, I double checked, but just a little bit messy. Okay, and I using the commutative rule again, I move this to the front, and then that, not x and not z, right? And then using De Morgan's law, and then equal to negative of that, the whole thing. So there's a negative sign there. Therefore, you have this minus this. So the formal proof is this. You have to go through this way, and not simply doing like I said previously, like this. So you simply, oh yeah, that's easy. How about this and that? If you direct write that, I'm not saying totally wrong, but it looks like you have to explain why the whole result is this. All right, hope that helps. Let me know if you still have some questions on this.